Howdy, welcome to Computer Graphics, Animation, and Simulation. In this video, we're going to talk about particle choreography. To begin with, we're going to talk about operators, what they are, and how they refer to particle choreography. Then we're going to talk about collision avoidance. Next, state vectors, and finally, flocking. So let's start out with a mathematical description of what an operator is. Essentially, a map, it maps set members to other members. So if you have a single set, like say all the integers, a operator would map one integer to another. For example, the arithmetic operator would, for addition, would add two numbers and return an integer. In other words, it doesn't return something different. In other words, you wouldn't add two integers and suddenly get a complex number. So the idea behind particle choreography came about from Carl Sims in 1990, and he wrote a paper called Particle Animation and Rendering Using Data Parallel Computation, which is an excellent paper to read. And in this paper, he suggested that there are several different kinds of categories of operators that we could use. Some of those could be initialization operators, in which we might decide, let's go ahead and put brand new particles in certain positions based on a certain behavior. Next, there's acceleration operators. This could be things like gravity or anything that can affect the acceleration of an object. And then, because this is an animation, we like to do physically, we like to do things that are not physically based. So there's also velocity operators, where we can do things like control the minimum or maximum velocity, or use it to determine or make decisions like, are we going to hit an object? Should we avoid it? Okay, so let's talk about acceleration operators. We kind of talked about initialization in a previous video. So in this slide, we have what's called an additive operator. And an additive operator is, we use this terminology where we use a superscript plus op. And the idea here is that we could have one or more of these operators. And if we just sum up their contribution, then we'll call this the net value. And so we have a few different ones that we'd like to use. The first is gravitational. So we might say that we'll just use the constant value for g as the acceleration, and then we would just calculate the force as normal. But we could also use the mass as use the general equation for determining acceleration for gravity using one of Newton's laws. And essentially we have that the gravitational constant times the mass of object A, which is the attractor. Okay, and that's what we're calling this, is a gravitational attractor. So we have this formula, minus g times the mass of the attractor divided by the radius or the distance squared between the attractor and the object I that we are trying to simulate. And then the vector x represents the direction from the attractor to the object I. And we can simplify this equation just slightly by saying that we can wrap up the mass with the gravitational operator, so we have a constant there, and we can generalize the power on the bottom. So if it was physically based, we'd use the square, but we could use the variable p instead, and we can control how much of this gravitational effect that we want to have. So next we have a random attractor or operator, and the idea here is we can use a random vector on a sphere. That's this s function. And we can use this to introduce a random acceleration on a object. So this could be, you can imagine snow, for example, that might have some updrafts from time to time. So we can use this to model those kinds of behaviors. And then we could also model drag. So maybe this is something inside of a fluid, or there's wind resistance. So we can use an operator to model the force of drag. So the next kind of operators are called velocity operators. And I like to describe these as breaking the law. In other words, these don't normally have any physically based reason for using them, aside from it could be a control for the animator. So one of these types of things we might want to do is a fiend velocity operator. We want to make a change to the velocity. There are other ways too. We could also just make sure that the velocity is clamped so that something doesn't go too fast or too slow. And so one of these that we could do is maybe we want to add an offset to the velocity, so translation. So we might want to introduce a velocity in a different direction all of a sudden. Or we might want to add a rotation to the velocity. That's another option. And then lastly, we could apply a scalar to the velocity so we can make something suddenly increase speed, for instance. So one other instance of velocity operator is a vortices operator. And the idea here is that instead of trying to simulate a vortex, we could use a function to simulate a vortex inside of a cylinder. And so here's a picture of a cylinder, and the idea is that we have the cylinder is a radius r, and depending on the distance from the base of the cylinder to the current projected height of the current velocity, so the current velocity is over here. So we can project how much rotational velocity should be on the vector, and we could use this formula for frequency is based on the distance r, so the radius of the cylinder, over r sub I, which is the distance from the vector to the center of the cylinder, times the rotational velocity at the edge of the cylinder. Okay, and this is a way of modeling a vortex without having to do the physical simulation part of it. So technically this isn't physically based, but it does give you that kind of a behavior, especially if you're just trying to get that look and feel to your animation. So let's go ahead and talk about collision avoidance. So collision avoidance, I'm going to talk about two particular kinds here, but essentially what we want to happen is we might have two elements in our simulation that we don't want to have collide. In other words, we want to avoid a collision because it's not natural for everything to kind of go straight through each other. So what we could do is use a potential field. And a potential field essentially is some kind of, we put some kind of force surrounding our object, and the closer you get, the stronger the force. And then the second kind is steering. So if we have a object flying towards another one, let's say we want to avoid the circle in the middle, then what we could do is we could plan a pattern around the cylinder so that it doesn't collide anymore. So maybe we're trying to make a actor act somewhat intelligently by not, say, driving into a roundabout and just cause them to go around. And so at this point, maybe we should stop real quick and talk about how do we represent these kinds of behaviors and values by talking about state vectors. So with state vectors, essentially what we're trying to do is keep track of important information that we need for our simulation, but we want to be efficient with this. So one way that we could do this is by using an array of positions and velocities. And even the order of how you put positions, velocities in the array can make a difference. So maybe we want to order the positions first, and then followed up by the velocities, and then perhaps even followed up by the accelerations, and keeping them so that we get that data localization. Secondly, we have some options about how to use these arrays, because perhaps we want to use a GPU. And if we were to use a GPU, we might need to use a texture map to represent the positions and velocities in an efficient manner. Next, we need to use a particle dynamics function. And the idea with a particle dynamics function is, say we have a system state vector that holds all of the state of the entire particle system, say we're interested in particle I, Well, the idea behind the particle dynamics function is to account for everything in the system acting to change the state of particle I. So this function is very important for handling this kind of behavior. And so next we have a system dynamics function, and the whole idea is that this is going to return the sum of all the forces that are acting on the particle system, especially when you're talking about the environment in between the particles. So this is to make this a more holistic type of simulation. So these functions are kind of crucial to integrating how everything is flowing together. And one particular example of using state vectors is with a flocking system. So let's talk about that. So flocking systems is one particular example of particle choreography. And this was introduced, or one of the major people behind it was Craig Reynolds in 1987 in his paper Flocks, Herds, and Schools, a Distributed Behavior Model. And he introduced this concept of boids, which is kind of a shorthand for birds, oids. But he used this so the system could be generic enough to handle other things like schools of fish and so on. So it doesn't have to just be birds. But in this particular example, we're just going to focus in a little bit on birds. And so the three things to know about this is, first of all, it's to model polarized behavior. So in other words, how animals kind of react. It's a zoological term. And then non-colliding. So of course, animals don't just run into each other most of the time. And aggregate behavior. So we're focused on what is the whole doing. So we can use actors to kind of represent the dynamics happening in this kind of a system. And in the case of birds, we might need this actor to have the ability to fly. And when we say fly, we're talking about geometric flight. In other words, the actual details of how do you fly. And you might include things in your model like wind resistance and flapping speed and so on. But it might also include things like banking. So how is this a boid turning? It could be in the water, it could be in the air. Secondly, collision avoidance. We need to specifically handle this so that the system is non-colliding. And velocity matching. So now we're working a little bit on aggregate behavior. So it's looking at its neighboring animal and deciding how to adjust its velocity. And also flock centering. So this is so that it doesn't spread apart. So it kind of keeps the whole system going together. So to recap what we've covered in this video, we talked about operators and the idea of particle choreography and some of the concepts. And you have initialization operators, acceleration operators, and velocity operators. We also talked about collision avoidance. In other words, you might have some like field type behavior where things act like it's either maybe attracting things or it's repulsing things. Secondly, you could have some kind of planning feature to avoid obstacles. Next, we talked about state vectors. So how do you represent operators? And we talked about different things like the particle dynamics function and the system dynamics function. And then we talked about an example of flocking, which is a specific kind of particle choreography where we talked about boids and several behaviors there that you have to keep in mind, and we use actors to kind of create the dynamics there in that particular instance. Well, I want to just say thank you for watching the video, and adios.